All right, going once, going twice.
$100.
All right, you get to grade them. So you get to pay me $100 to grade them. It's like Tom Sawyer. The TA will be very happy to hear that. Okay, so this is now, we're going to start with the material that's going to be covered in Exam 2. The TGOs that are due, that are covered today are not due until this coming Thursday. I'm sorry, next Thursday. So focus on the exam material. So we're going to be going over these two algorithms known as restoring and non-restoring division to start out. So there's pros and cons to each of these, and as we're going through the algorithms, I want you to kind of think about, now that we're understanding advanced digital design and kind of the underlying principles between them, the trade-offs that we have to think about. We're just start thinking about, well, what's the positives of this restoring division, and what are the positives of the non-restoring division? Because on the exam, I'm going to give you a problem, and I'm going to say, you have to tell me, you can do restoring or non-restoring, but you have to tell me which one it is, and then it has to be that algorithm, right? So let's say you write restoring division, and you do the non-restoring division algorithm. Many points will be, many lives were lost to get these secrets, right? The Star Wars. So restoring division. So which one is so if I have 9 divided by 4, which one is my dividend and which one is my divisor? Good. You guys are way ahead of the curve. Usually I get a lot of blank stares from students when I ask that question. It makes me feel good that kindergarten's being taught better. Or second grade or whatever it is. So basically the divisor is the one doing the verb, doing the action. So now we have our output is going to be a quotient remainder. So if we have 9 divided by 4, our quotient is going to be 2, and our remainder would be 1. Okay. So we initialize our quotient of having n bits. The same thing that's going to be on your exam with sign division. It will be no bigger than 4 bits. The remainder is going to be n plus 1 because we're going to be worrying about sign. And quotient, we can initialize the quotient to equal the dividend, right? So if I had 9 divided by 4, this would be 1001, and my dividend is going to be set to that. Because what's happening is we're going to be using the most significant bit from the divisor, and it's going to pop off onto the remainder, and we're going to be using this remainder to be able to perform a repetitive addition or subtraction, just like Thomas Hobbes talked about at the beginning of the section. So from I equals 0 to n minus 1, so we're going to do this n times. So we have this remainder that's initialized to 0, right? That's 5 bits. And we have a dividend. The quotient is now set to the dividend. So we're going to left shift the remainder, and the most significant bit of the quotient is going to become the least significant bit of the remainder. So what that means is this result is going to be left shift. So, and then I have a bit there at the end where I'm missing. So now we're going to left shift this one as well. And the most significant bit of the dividend, of the quotient, is now going to be the least significant bit of the remainder. And then remainder is going to be 1 minus the mantissa. So what that means is we're now going to have our mantissa, which is equal to our divisor. So that would be 0, 1, 0, 0 for 4, right? So we'd subtract it. Right, that's our 2's complement, right? So we're going to subtract it. Right? And now we worry about the most significant bit here for the rest of the algorithm. So the left shift, we're going to left shift the quotient, and the most significant bit, I'm sorry, I should have that up here because it should be 1, 1, 0, 0, 1. I think that was the result, right? And so we had this quotient that we left shift. And so we took that most significant bit of 9, and we have 0, 0, 1 left. and this value here. And we're going to be going over an example of what I mean by this. Is the left shift to the quotient and the most significant bit of the remainder, which is this value here, 11001, is the negation of the least significant bit of the quotient. So what I used to do when I took this course is I would circle it, do some sort of negation value here, go like that, and put 0 as the least significant bit of the quotient. And then if the most significant bit of the remainder is equal to 1, then we're going to restore. Now what that means is we subtract 4, and then we're going to add 4 back. Right? So we started out with this, we started out with 0, 0, 0, 0, 1, right? And then we subtracted 4, so that became 1, 1, 0, 0, okay, I just want to make sure I was doing it right. So what do you think a common mistake, if I'm adding 4 to this number here, what do you think a common exam mistake that students do is?
Add wrong.
Correct, add wrong. But what's the solution going to be? If I'm going to subtract 4 from a number and then I'm going to add 4 to it, what's the solution automatically going to be? Bingo, this original number. So you just go add. Don't even worry about it. That saves time, saves the ability to make a mistake on calculations. So that is what's known as restoring. So then the next, we're going to shift again, 0, 0, 0, 1. And now we have this quotient over here. We have 0, 0, 1, and we had 0, right? And so we'd left shift again. This becomes 0, 1, 0, blank. This 0 here becomes that. We subtract 4. We're going to get 1 again, and so forth. And so what we're going to find is that quotient, you see how that 0 became the least significant bit? That's going to shift over, and eventually that's going to be the most significant bit of our quotient. And since our solution is going to be 0, 0, 1, 0, because it's supposed to be 2, that means we did the first step correctly. So let's go over this example. It's always going to take 4 cycles. So in this case, the question is find 8 divided by 3 using restoring division. So first we find a remainder. We set it all to 0. It's n plus 1 bits. We have our quotient, which is 8. Our mantissa, which we set to the divisor, is 3. And the 2's complement of 3 is going to be 1, 1, 1, 0, 1. And the reason why you want to do the 2's complement initially is because you're going to be subtracting, and then you're going to be adding if the most significant bit of that result is 1. So here, we're going to left shift. We're going to have this value here. So this becomes 1, 0, 0, 0. So we have 0, 0, 0, 0. Everything's shifted left. Then we had 1, 0, 0, 0. The most significant bit of the quotient becomes the least significant bit of the remainder. Like that. That's what's going on there. And then we subtract the mantissa. And so that's the 2's complement of 3. This becomes 0, 1, 0. In this case, since the most significant bit is 1, we're going to do 2 things. First, the negation of the most significant bit of the quotient is going to become the least significant bit. Of the remainder is going to become the least significant bit of the quotient. So we have our quotient here is 3 bits. This comes over, it's negated, and it becomes 0. And that's what's happened here. Now, since it starts with a 1, that means we're going to restore, which means we're going to add 3. So what's my value going to be here? Yeah, it's going to be 0, exactly 1. Right? So our first step, we had 1 and 0. So you guys did it correctly. That's our first step. So for the second stage of the algorithm, we start out here with this remainder and this quotient, right? So what's the first step of the algorithm? Shift left what? Okay, good. And now what? Good. You guys are picking this up fast. All right, so now I have 3 here, right? And so now what do I do? I'm sorry? Oh, that's not quite yet.
Oh, subtract.
Yeah. Good job. So we got 1, 1, 1, 0, 1. And this becomes, now what do I do, Meg?
Negation of the most significant.
Becomes what?
The least significant bit of the word.
Good. So that's the remainder, negation. And since we know it's always a good idea at the beginning of these problems, you do 8 divided by 3. That's going to be 2 with a remainder of 2, right? So our quotient is going to be 0, 0, 1, 0, and our remainder is going to be 0, 0, 0, 1, 0. Okay. So these 2 bits are going to correspond to these 2 bits because they're going to continue to left shift. So now we know that we've done our first 2 steps of the algorithm correctly. So what's the next thing we have to do in this case? Add it back, right? And why are we adding it back? Restoring. Why are we restoring? To get it. Well, I mean why are we restoring the remainder? What part of the algorithm corresponds? What? Yes, good job, Leah. That's what I was looking for. The most significant bit is 1. Therefore, we restore, and that just simply comes back to the number we had originally. Right. And as you can see, so far we are doing it correctly. Third stage, again, so we start out with, and our quotient is this number. So what are we doing? And then, job time Latches. And now what do I do? Subtract. And so this becomes 0, 1, 0, 0, 0. Don't worry about the carry. So what does this mean? So now what do we do?
Are you doing cycle 3?
Yes.
It's 0, 0, 1, 0, 0. Right?
Yeah. We shift left. And then, so by shifting left here, this is our initial value. We shift left.
Where's that on the screen?
It's right here. Cycle 3.
Okay.
Right there. That corresponds to this. But then in order to get to that point, what we need to do is we have to shift left first. So the first stage of the algorithm, we have to take that value, the current value in the divisor, that's the remainder, shift left, which is how we got here. So I did this for clarity, but I'm writing it on the screen. So we have the correct value here. So what do we do next? What's our next step? Well, we're missing one thing before we do nothing. Yeah, we have to, no. Sorry. It's 0, therefore, there's... You don't restore, but you notice how that's only this part of the algorithm? We still have to, you do that every time. The if statement is the restoring. So you can go back over here. So back to stage 3. So see how we take the most significant bit. I'm going to scroll up a little bit for those in the back. So we take the most significant bit of the remainder, negate it, and it becomes the least significant bit of the quotient. And so there's our 1. And since our result's going to be 0, 0, 1, 0, and we have our first 3 bits, we know we have done it correctly. Now what do we do, Joseph?
Nothing.
Good. We do nothing. We leave it alone. Don't add. Right? So we've left it alone. And so our final stage, we shift left because it was 0, 0, 0, 0, 1. We shift left, so it's 0, 0, 0, 1, 0 because we get our 0 from our most significant bit of the quotient. We subtract 3. We get all 1s. We take the most significant bit of the remainder, negate it, make it the least significant bit of the quotient, It is 0, 0, 1, 0. That is the answer that we expected. Therefore, that's what we want to do. Now, last step, and this is why it's called restoring division and why the restoring is important. So here we have this value. What does that value correlate to? If we took the 2, I'm giving you a big hint. If we took the 2's complement, it would be, right? So is that, but it's a negative value, right? So the result wasn't 2 with a remainder of -1, right? And have you ever, in any of your mathematics, ever had a negative remainder when doing division? Okay. The reason why we do restoring is because you want to get to that point where your remainder is going to be starting with a 0 because you want your remainders to be positive. So what we do here is we're going to restore by adding 3 again, and we're going to get 2. And so our result, quotient is 2, remainder is 2. So therefore, our solution is correct. Does anybody have any questions on this before I go on to non-restoring? Yes?
So I'm a little embarrassed to admit this, but I don't know what you mean by left shifting.
Oh, sure. Okay, no, so. All right, so let's say I have 0, 1, 0, 1, 0, 1, right?
Is that a string or an array?
It depends on what they're defined as. So you can define this as an array. A string is an array of characters. So but let's say I was defining this as Booleans, it would be an array. So in this case, if I want to left shift, what I mean is I want all these numbers over here moving over by 1. Right? So that's what's going on here.
So you fill in the 0.
Mm-hmm. Now, here's why left shifting is important, especially because when we're doing with byte addressing, we're going to need to multiply by 4. Remember I was talking about load and store word a few lectures back? If not, that's okay. Okay, so I talked about it, and I promise you have to multiply by 4. So if I have the number 3, and I want to multiply by 4, I can go through this complicated sign multiplication algorithm, which you guys learned last lecture. Or I can left shift by 2, because in binary, every time I left shift by a value, I'm multiplying it by 2. So if I'm multiplying it by 2, now that I have 2 to the 3, which is 8, plus 4, which is now 12. So we've now multiplied by 4 in a simple way. So you can, instead of having to do n plus 1 cycles, you can now do that in 1 cycle. And so that's where that becomes important. Shifting right is like dividing. So now I have adding the 0 to the left. And we have that. So the reason why we're doing this is, you recall at the very beginning, I had this quote from Thomas Hobbes about everything's addition and subtraction. So what you want to do is you're trying to see first, can you subtract 3? Can you subtract 6? Can you subtract 9 from it? And you're trying to do this again, because basically 8 divided by 3 is, first I have 8 minus 3, which is 5, right? So that's still greater than 3. So we have 1. And then 5 minus 3, which is 2. So now it's 2. So now we're just kind of taking that result and subtracting it. And then since 2 minus 3 is -1, that doesn't work. And therefore it's 2 with a remainder of 2. Yes?
So if you shifted left 3 places, would you be multiplying by 6 or 8?
By 8, because it's factors of 2. Yeah, think of it this way. Okay, so it's a binary, right? So if you're, let's say I have this by 10, right? And I shift left, to make it more clear, let's make this 16. And I shift left in decimal by 1. This becomes 160. So I'm multiplying by 10. I shift left by 2, it becomes 1,600. It becomes 16,000. Same thing, if it's 1, 1, this is 3. If I shift left by 1, it becomes 6. If I shift left by 2, it becomes 12. These are good questions. So it becomes important if you if you actually really understand what's going on here, then the algorithm becomes more intuitive as you work through it a few times. Any other questions? Boring some people to sleep. So here's non-restoring division algorithm. This is a little longer. I've just made a little more spaces. It's not that bad. So the difference is we're going to make a decision halfway through the algorithm about whether to add or subtract. So we're taking that most significant bit and deciding whether or not we're going to add or subtract. And in the previous algorithm, we subtracted every time. And then what happens is we're trying to manipulate the remainder. So every stage in that algorithm, if we had a 1, we subtracted, then we added back, right? And so here, we're just going to add or subtract, and then move on to the next loop. So we have we initialize it the same way, divisor, dividend and divisor, remainder is going to be equal to 0, quotient is equal to dividend, mantissa, n plus 1 is equal to divisor. So it's the exact same initialization. First, every cycle would do the exact same thing. Left shift the remainder, and the most significant bit of the quotient becomes the least significant bit of the remainder. Now here's where the algorithm is different. So now if we check that most significant bit of our remainder. So if you remember from our previous problem, we had 0, 0, 0, 0, 1 after the left shift, correct? So now we're checking the most significant bit. If it's 0, we're subtracting. If it's 1, we're going to add. And so then, just like before, left shift the quotient and the least significant bit. And so the most significant bit of the remainder becomes the least significant bit of the quotient, but negated, just like before. So this initially appears faster because you don't have a second addition, right? We have to compensate. So we go through our loop. So we see we have our brackets here that indicate the end of the loop. But then I have this little step here at the end. I'm going to scroll up for those in the back because this is important. Now we get to this point at the end where if the most significant bit of the remainder is 1, we're going to add the mantissa. Why would we do that? What's the issue if we have a remainder that starts with a 1?
It's negative.
Yes, right? So we have to get rid of that and we do it by adding. Turn on the volume light. Maybe that might be a student email. It's not a student email. Right, does anybody have any questions on this? We're about to go over the example. Right. So, non-restoring division. So here we initialize it the same way. We're doing the exact same 8 divided by 3. And what we're doing is the remainder is going to be 0. Our quotient is going to be equal to the dividend. The mantissa is going to be equal to the divisor. And again, I always state the 2's complement. Allows me to keep track of everything. So cycle 1, we have 0, 0, 0, 0, 0. We're going to left shift by 1. And then the most significant bit of the quotient is going to become the least significant bit of the remainder. And now we have a left shifted quotient where we have not replaced the least significant bit yet. So what's going to happen is we're going to, since it's 0, we're going to subtract. So if it's 0, subtract, 1, add in this algorithm. So here we subtracted, and we have our 11101. We get 11110. Then the most significant bit of the quotient becomes the negation of the least significant bit. Sorry, the least significant bit of the quotient is the negation of the most significant bit of the remainder. So it's a 1, we negate it, it becomes a 0. And then we're done with that cycle. So cycle 2, we have 11110. So what do we do? And then we have a quotient of 0, 0, 0, 0. Yep. And then what? Mm-hmm. And now what do we do? Should be clear that the value we pop off here is the value we test. So in this case, we're going to add. So we're going to do 0, 0, 0, 1, 1. This becomes all ones. And so now what do we do?
Move the 1 over negated. Put it at the least significant bit of the quotient.
Bingo. And we're done. Right? That's a typo, by the way. All right, so next stage, we have 1, 1, 1, 1, 1, and then 0, 0, 0, 0. Shift left, so 1, 1, 1, 1, 0. And now what do we do? Add, right? Why are we adding? Somebody besides my 3 people who have been. Yeah, exactly right. So now, right, it's going to keep, the carry's going to keep going. So then, what do I do? And since this is going to be the first 3 bits, and we're expecting 2, we're on the right track. And that's it for that cycle. And then last, certainly not least, we have 0, 0, 0, 0. We had 1, and then 0, 0, 0, 1 here. So what do we do? This one, everybody should be able to say it. And then?
0.
Yep. Very technical way of describing it. 0 right there. Since it's a 0, what do we do? Subtract. Now what do we do?
Move the 1 over.
Yep, got to negate it. We got 2 on our 4th cycle. Therefore, we know that's correct. And so we end the cycle there. So what's my last thing that I need to do? Mantissa? Why? Bingo. So now we're at our last, we've passed our last cycle, and we now have to do this one last check because of our negative remainder. So now we just, right? And recall, just like restoring division, it's going to be the same thing as getting this previous value. As you can see, we had 2 already, so we have the right answer. Yes?
I guess at cycle 2 you ended up with 2 already. Now I guess you're solving for the remainder and those last.
Cycle 2, we ended up with 2
quotient.
Oh no, that's a typo.
Oh.
Like I said, that's a typo.
Oh.
That should be 0, 0, 0, 0. So here it's 1, and now it's 2. Yeah.
But if you did get the right answer,
Well, here's an interesting exam type thing. What if I did get the value of 2 here? I did some sort of math thing, and I got a value of 2 there. What does that mean? Yeah, you made a mistake, and I can tell you precisely where you made your mistake because of where your first incorrect value is. So if this was 2, this means this would have been 1 here. That means I can tell you that you screwed up your math right there. So instead of doing the student panicking thing, where I'm erasing everything, trying it again. There's where you made your mistake.
Is it usually 4 cycles every time?
Yes, by definition.
I guess for 4 bits, it'd be 4 cents.
4 bits for 4. I will define it. In MIPS, how many cycles do you think this requires?
32.
32. On an exam for time, I'm limiting it to 4.
Now, I guess if you don't have a remainder, that would just be 0. I guess.
That's what is this value here?
Negative.
Yeah, negative
15.
No, not negative 15. It's negative 1, right? Because it's 2's complement.
That's good.
So, but when you were in 2nd or 3rd grade and you learned division, did you ever have a negative remainder?
No.
Correct.
I mean, I'm saying what if those 8 divided by 4, you would have no remainder. That's what I meant.
Yeah, it would be all zeros.
Okay.
If it's all zeros, just leave it alone. It has to start with a 1 because 1 implies negative. That's what the if you go back to the algorithm, and that's the reason I have you guys write the algorithms out. Most significant bit of the remainder is 1, then do something. Otherwise, yeah, just return the values. Does anybody have any other questions about restoring and non-restoring division? You guys picked it up awfully fast. In the past, I've actually spent an entire lecture on just those 2 examples. So it makes me but those students actually did very well on the questions on the exam. So that's why, hence my hesitation to move on. I just want to make sure that's how willing I am to answer. Leo, do you have a question? No. That's how willing I am to answer questions about this. Like I've done a whole lecture on it. So, okay. All right, so that's the end of section 3. So let's get started in section 4. So we're start talking about sequential circuits and finite state machines. So we talked about this very briefly in section 1 where we defined sequential logic, and we defined. So for those of you who are looking over your quizzes and seeing where you lost points on the definition of a digital system, most of you correctly said that there were digital inputs and some sort of operation and digital outputs. But where many of you lost points is the recognition of a state, some sort of memory element. So you want to say that the digital circuit takes in discrete inputs and has state memory elements, and based on that information performs some sort of logic operation and has outputs and updates the state. Full credit, even though that's not word for word, right? So the previous TGOs were 1.3 through 1.12 and example problems 1.1 and 1.2. So in an amusing twist of fate last year, I was over at the student union right before I was giving my lecture on this, and I went to get a Coke, and I noticed something really interesting. I put in $1 into the machine, and the machine initially rejected the $1. And so then when I put it back in, but then pressed the button, it decided to reject my $1, but still vended the Coke. Okay. So I did it a couple of times, did it again, so I suddenly had 3 Cokes. Now the Coke vendor was there, and I said, hey, I actually didn't pay for these, and I gave them back. Most people would look at the situation and go, free Cokes! I look at the situation and go, I know what's wrong with the computer. The finite state machine is broken. I can use this for a lecture. So he crumbled $1 and managed to replicate the error. He reset the device and restored proper operation. Now, if I hadn't found this at 7:30 in the morning, you know what would happen? You'd have thousands of students just getting free Coke. So sorry about that. I know you all want your free drinks. But the problem thing is that's good for students, not good for the poor guy who's supposed to code the finite, the poor lady who's supposed to code the finite state machine, which might be you since this is an electrical engineering problem. They come back and you screwed up. We just lost thousands of dollars. And if you have the wrong boss, suddenly you've lost thousands of dollars, right? So how do we avoid these kinds of things with thorough testing and timing issues? So here, this is a very simple Moore machine. Okay, you guys remember those problems you did in section 1 with Mealy and Moore machine? That I hope you do, because you may need to know that on Tuesday. You'd be able to follow a Mealy or Moore machine. You consider the simple Moore machine where we have states A, B, and C, right? And so we also have transitions and what the value is when we get to the state. And the Mealy machine was different. It's where we had this 1, 0. So if we traversed along this path, it was a 1. If we could traverse along a different path, it was a 0. So that was the difference between Mealy and Moore machines. So here I'm going to give an example. And this actually, Brian, this actually will answer your question that you asked a little earlier about strings. So here I've actually coded up the finite state machine in C with a set of inputs. So I have a integer of input strings. I can initialize that array. And then I want to have an output string, right? So I have length. I've initialized an output string pointer because I want to create an array. I've used calc. And my calc is length, comma, size of integer. So now I'm allocating a size of integer times length to create this integer array. And what does calc do? Sets them all to 0. And then I initialize our current state as 0. So I have 3 states here. So I have a switch statement. So I define the current state as state A. So we go back up here. I define them as state A, B, and C. And the reason I did it as A, if I may be able to zoom in here a little bit. Did it work? Yes. See, I have this little reset value here. That anytime you have some reset equals 0, that means you're going to start over again. So we go back to our Coke machine example. You bend the Coke. It should then go back to the initial state because the finite state machine and the Coke machine represents the amount of money that the user has put in. So if you put in 5 cents, you're going to go from free, you're going to traverse to state B, which indicates you put in 5 cents. You would go to a different state if you put in $1 initially. And so what was happening was, in this particular finite state machine, if it's the bad dollar, it's supposed to reject the dollar and go back to the previous state. It was rejecting the dollar. Instead of going to the previous state, it was going to bend the final state. So that's where understanding this coding becomes important. Make it a little smaller, a little bigger. I like Goldilocks. Yeah, there we go, just right. So here I have my code, and I have my initial current state of A. So then if I had in that state, I said that if you get to state A, the output is 0. So that means I said output string of I is equal to 0. I have a for loop. So the number of inputs I have in my input string is the number of times I'm going to go through the finite state machine. So somebody submitted a solution to the coding challenge with a finite state machine, and I took points off because they hard-coded the states, and I wanted a for loop. So they actually said go to this state, go to this state. The purpose of the finite state machine is you're not going to know the inputs. Once you get the inputs, then you have to make decisions. So for example, you can't guarantee that the user is going to put in $1 and put in a quarter every time. They might pull out a pocket full of change, and your finite state machine still has to work 100%. So here, what we've done is I set it. I'm going to increment every time I go through the loop. So I'm at first state, second state, third state. So when I'm at state A, I set the output string to 0. So recall we have 0, 1, 0, 1, 0, 1, 1, and in A I set 0. And then if that input string is equal, okay, so then I'm initializing the next state, right? So I probably could have just said cur state 1, right? But basically, if it's case 0, it means I'm going to the current state, and then I want to go to check my next state. So remember, if it was 0, we just looped back to A, but if it was 1, we went to B. So in this case, I have A corresponds to state 0, B corresponds to state 1, and C corresponds to state 2. Here, if I go to B, again, B is 0. But if the string is equal to 0, I'm going to go back to A. So in this case, A is 0, B is equal to 1. If B is 0, it goes back to A. If it's 1, it goes to C, which is what I find as current state 2. And then case 2 means state C. That means the output's going to be 1. And then if it's 0, I want to go to A, and otherwise I want to go to C. So C, it's staying to 1. There's no path that goes from C to B. And then as my default in my switch statement, I want to have standard error invalid state assignment. So for some reason I got case 3, instead of inadvertently bending the Coke, I just print an error to the user. And so then I have a for loop where I print the results to the user. And since I did calc, as you can see, the last thing I do is I free the output string. And so here's my compile statement. And so I printed the inputs and the outputs to the stream. 0, 1, 0, 1, 1, 1, 1, 0, 1. And then I got the sets of outputs, which are the correct value. Because you'd be going to, you start at A, you go to B, still going to B, and eventually you finally get to C here. The C goes back to A, which is our correct value. All right, so if you recall, for Creativity Challenge 1, I accomplished the same thing for a Mealy machine. We did that last week, and I posted the code solution. I had the solution for the code and my example write-up. So if you want to look up and see how that's done using a Mealy machine, you can go into Blackboard and do that there. And so here, this section is going to help these course objectives that I stated in the syllabus: combine medium-scale integrated circuits into larger and more complex digital circuits, learn the various design methods and see the description of a sequential state machine, and use current engineering software to compile and simulate circuits, including those described in C. Now, something happened in the news today where somebody was using sequential state machines, yesterday, used sequential state machines to code onto a circuit board to do something, and it became a huge news story yesterday. Does anybody know what I'm kind of alluding to? Yeah, exactly. A kid, he coded state machines to be able to perform upcounting, right? And he probably used gray code because, remember, we were talking about race conditions? So he coded it using gray code, and it was clocked, and it worked properly. And he went in, tried showing it to his engineering student, and his engineering teacher, and then other things happened. So, finite state machines in the news. So, it's not our fault. Other people are stupid. All right, so there are things you have to worry about when talking about sequential state machines. This is kind of a review. Latches are asynchronous, level-sensitive sequential storage elements. What do I mean by level-sensitive?
Circuit changes its state and output information relating to changes level.
Okay, so we're going to be a little more specific. I see what you're saying. I'm kind of talking about, I talk about edge sensitive in 4.4. So in a digital waveform, we have an edge and a level. So it just changes, it can change at any point here. Now, where we're talking about edge sensitive circuits, they can only change here in the circuitry. Now, if they can change here, that's known as a latch. So a level sensitive circuit changes its state and output whenever the input changes level. So here it changes the level, but here's the thing. If you have another value change while it's still there, then it becomes problematic, and that's where you can start getting race conditions. So if you're doing latches, you have to be very, very careful on timing. You're not gonna. That's it. Remember that problem you did on the quiz where somebody tried ramping up the it was the clock cycles from like 2 to 3 or 2 to 5 or whatever, 2 to 2.5, right? If you have a bunch of latch circuits and you try doing that, your computer is going to go to crap. So that's why a lot of these finite state machines and memory elements are going to use edge-sensitive circuits, because you can avoid those by doing it just on the edge. And so in order to do that, 4.3, we're going to use flip-flops. Okay. A flip-flop is called aka gated latch. Is a synchronous edge-sensitive sequential storage element. And in order to implement that for 4.4, we're going to use what's known as an edge-sensitive circuit, which only changes if it goes from 0 to 1 or 1 to 0, only during that change. And we're going to describe how that's physically done in a little bit here. So 4.3, flip-flop, aka gated latch, is a synchronous edge-sensitive sequential storage element. And 4.4, an edge-sensitive circuit changes its state and output information only on a single type of level change. And what that means is it will either change from 0 to 1 or from 1 to 0. We define positive edge as level from 0 to 1, meaning it's going to positive, or negative edge, meaning it's come from 1 and going to the negative value. So we define those in that manner. And so what we're going to be doing for the next few topical guide objectives is we're going to discuss certain latches physically, and then we're going to describe how they're modified in order to make them flip-flops. So if you all recall SR latch, SR flip-flop, D latch, D flip-flop, T latch, T flip-flop, and eventually what we're going to get to is we're going to get to the JK flip-flop, and we're going to see all the pros and cons of all these different latches and what the JK flip-flop does to address all of them, and why it's kind of, there's a reason why its designer won a Nobel Prize. It's pretty ingenuity. All right, so let me scroll up a little here and start talking about SR latch. So the topical guide objective includes the finite state machine, the truth table, and the physical implementation. And there's a reason I'm doing this. So the SR latch, if you start, I call it A and B, but basically, and the transition states talk about 0, and this is S and R, set and reset. So this is S and R, that's S and R, and that's S and R. And that, does anybody know what this X stands for?
Don't care.
Don't care. It means I don't care what it means. In this instance, this transition means that whenever S is 0, I don't care what R is, it's going to move to this representation of the output. Now, this representation of the output, either you're going to have Q is equal to 0 and Q bar is equal to 1, or Q bar is equal to 1 and Q is equal to 0. So why are they not the same? What does bar stand for? Not. So if you get Q equals 1 and Q bar equals 1, what has happened? You've made a mistake. Now I'm going to tell you guys a Navy story here. So this is one of those things where students will come back to me like 5 years later. It's like, I loved it when you told this story. So I was taking a circuits class in nuclear power school, and Senior Chief Bennett was the instructor for that course, and he sounds a lot like Marvin the Martian. So we were talking about SR latches, and you have these state machines, and you're trying so hard not to laugh because he's being deadly serious. So a common mistake that students would do is they would try to design the circuit. Let me scroll up so you guys can see. So it's 2 NOR gates in a sequential element. So you have R and S and Q bar. So a common mistake is somebody would work through the finite state machine, they would get to the end, and they would have Q equals 1 and Q bar equals 1, or Q equals 0 and Q bar equals 0. So they have some of us come up, so Petty Officer Morrison, or it wasn't me, but somebody else in my class, comes up and designs it, comes out with a solution, Q equals 1, Q bar equals 1. And he just looks exasperated, and it's, the way that it works is like this. It was down here, there's a table, so if I had a table here, I'd be up on that kind of level lecturing down. So he gets up on the table, like so, and he's kind of a short man, like so. And he goes, all right, I'm going to say this once, and this will be the only time I cuss in front of you guys, right? Q never, ever, 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 fucking ever equals Q naught. I've never made that mistake again. So, does Q equal Q naught ever? No, right? That is why 0, 1, 1, 0.
Are you going to do that?
Am I going to do that? Don't have 0, 0, or 1, 1. All right. So here in this case, what 0 set and reset, if set and reset are both equal to 0, we have the state initial is the same. So if it was 0 and 1, it's going to stay 0 and 1. If it's 1 and 0, it's going to stay 1 and 0, right? If set is equal to 0 and reset is equal to 1, that means it's going to be 0 and 1, right? That means I want Q to be equal to 0, and I want Q bar to equal to 1. So if I have set is equal to 0 and reset is equal to 1, these are NOR gates. So what happens if it's 1, it's automatically going to be 0 here. 0, 0 is going to give me a 1 on the output. Now, I want you to notice how this had to wait for that to perform, right? We're going to talk about how that can be an issue in a little bit. So if it's 1, 0, it's going to be the exact opposite. So if I have 1 and 0, it's going to become 0 here, and that becomes 1. And then if I have 1, 1, that's weird, right? I don't want them to be the same, right? So I have this little undefined value. So if I do 1, 1, then I'm going to get zeros there. So that's not good. We don't want that state. So eventually, when Jack Kilby was designing his JK flip-flop, he was bearing this in mind. So let's go to our physical elements. So let's see if I had a compiler drove that by loading the physical elements into memory. We want to be able to save Q and Q bar values for the duration of the program. So now I've kind of gone over what a struct is, but I want to be able to define them so you can kind of, I said in previous lecture that I realized I had made a mistake by not defining them, so we're going to define them here. So 4.6, you want to be able to hold on to these values. So a struct is a collection of many variables, possibly of different types, grouped together under a single name for convenient handling. And for those of you in the front, you can see I actually have a I have a struct there. But I'm going to describe what it is. And a type def allows you to form complex types from more basic machine types. So if I have an integer and a string and a few chars or some sort of representation, like I'm trying to define a person in a database, I can actually create this structure to be able to access those pieces of information in C. I'm going to describe this in a second. So type def, again, allows you to form complex types from more basic machine types and assign simple names to such combinations. So here I have done, this is the difference between a type def and a structure. So structure, I'm going to move this just up here. So structure just has struct, SR latch, so, and then you have brackets, and then I've called them bool Q and Q bar. And the reason why we're doing this for memory elements is because when in combinational elements, they just move along, whereas memory elements, I want to be able to save them and reference them later in the program, especially when you're going to be designing a data path. And so the difference is I can now define this and call it using a type-def structure by adding this type-def keyword before struct, type-def key struct srlatch bool q bar, and at the end, here in all caps, I have srlatch. That means if I can actually define using a type-def, I can do all caps srlatch, the latch, right? This will compile. And if I were to assign a q and q bar value, I could actually say, the latch dot q and get the value there. And so here I have included std bool. You want to include your structs in your header files. So here I have some sequential elements here. I've called it that, struct, srlatch. And now we can actually talk about how to assign and get values, and, which I'm sure you guys will be super excited about this, how to assign and get them when using them as pointers and functions. So in 4.8, so that's a type-def struct. To assign a value to a variable within a struct, use struct.variable. So I had srlatch, right? So as that big dot q. So if I could say that's equal to 0, and then I'll assign q is equal to false, and then if you did q bar is equal to 0, then Senior Chief Bennett will come over and start screaming at you and cussing at you like Marvin the Martian, right? So now let's say you want to pass that variable to a function. You can pass the function, you do the ampersand like normal, but then when you call it in the function, you're going to use your arrow. So you do these two characters, it's like a minus sign and then a greater sign. So when a struct is passed to a pointer, to dereference a pointer for variable within a struct, use struct arrow variable. When a struct is passed as a pointer to a function, to access the variable, you will need to use the arrow again to dereference the pointer. So just like in your functions where you pass a variable as a pointer to a function, and in order to operate on the function in the code, you actually had to have the star and the variable equals 5 in order to dereference the pointer, to update that copy of the variable in memory. To do that using structs, you use arrow. And what I mean by arrow is it would be srlatch arrow q. And so I'll have some code examples here in a second. And so here I use srlatch as a pointer to combine the concepts. So I'm now doing the physical implementation. I have an srlatch where I have bool set, bool reset, and I have a srlatch struct. So I have a structure, and then I have a function which performs the operation. So remember, C is a procedural language. So in C, you actually have a function that will perform the procedure. In an object-oriented programming language such as C++ or Java, you could create a function within class srlatch that would perform this. So you would just put this function in your header file and perform the procedure. Now the benefit of that, now if you remember from section 2, I talked a lot about how C compiles down to the machine code. Now let's say I have, let's say we're going to talk about SRAM in a little bit here. So let's say I have 32 SRAM for one array, and then I have 32 registers. So an array is a register, and then I have 32 registers. That's what's going to happen in NIPS. For an object-oriented programming language such as C++ or Java, if you created a function like this, you would have to create a location in memory for each one of those SRAM for the function to be able to perform that because it's part of the class. Whereas here, in the procedural language, you're just passing the structure and you have one copy of the function. It would just perform a jump. We're going to learn about this next section, a jump instruction to that function, perform it, and then return the values and go back. So that's how you're able to reduce the machine code. That's why if you do hello world in C, it takes 28 bytes. If you do hello world in C++, it takes 1,000. So here what we've done is I've passed an SR latch type def to this function using a pointer. And then here I have two XORs. So remember in this programming assignment that's due on October 4th, you're going to be designing XOR gates using switch statements. So now I can build on that and pass them along. I can do R, and I call Q bar by using the arrow. And then I have XNOR S latch arrow Q. And that's actually passing the pointers like we normally would. And then it assigns Q is equal to R XNOR Q bar latch Q bar Q. That actually should be or, that's a typo. You see in the TGO, it is or. And so I have the printed values out here. Now, I want to show you a Vhdl simulation of SR latches and some issues with them. So here you can see I have 0, 0 before we've initialized it, and we have these weird things going on here, right? And here we get to 0, 0 again, and I have this weird stuff going on. It's flipping back and forth. But remember, in that value, I'm sorry, if it's 1, 1, then, but remember that Q and Q bar are the same. But why do you think this is happening?
It's racing.
Yeah, it's racing, but why do you think it's racing? But you're on the right track.
Because it's a NOR gate, and every time you don't have a 0, 0.
So what's going to happen? So if it's a NOR gate, and I get a 1, what's going to happen? To put a 0 on the other one, right? Because it's a sequential element. So then it's going to put, I get a 0, it's going to flip that value, it's going to move it over, and it's just going to keep rolling and rolling and rolling and rolling and rolling. So now I can see why Joseph said race conditions, because I had giant race conditions people can read. And so exactly like we were saying, you're just updating the value and it just keeps changing. So there's a way to get around this when coding it in C, which is to use in that finite state machine, which is why in the TGO I've included, all the way back here, I've included your finite state machine, I've included your physical implementation, and I have included your truth table. So now you can use all of these to properly design it based on what you want to accomplish. So here I have designed SR latch FSM. I get bool. I've done the same thing. I've passed the latch type def struct by reference. So if S is equal to 0, if R is equal to 0, that means it stays the same, right? So here I don't have any code for it. I just ignore it. There's nothing here. But if it's 1, I want Q is equal to 0 and Q bar is equal to 1. And if S is equal to 1 and R is equal to 0, then latch of Q is equal to 1, latch of Q bar is equal to 0. And then I can put bad Boolean input for other cases. Because you don't want a situation where you're getting 1 and 1 in both of them, because set's equal to reset in that case. And so then the result, I've coded up my SR latch test. I've done a number of cases here. I initialize Q and Q bar to be opposite values. And so then I have a number of fprintf statements where I'm calling my srlatch FSM procedure. I'm passing my type def struct of srlatch, which I've initialized here, using an ampersand. And then I'm updating the S and R values. So I'm putting in different values, and then I can print the results here by doing fprintf. And so I've gone through all of these. I go through like the whole case, and I put in a number of S set is equal to 0, R is equal to 0, just to see if it would change after any case. And then, as we can see, we did not update when S is equal to 1, is R equal to 1, because we have protected it. So then quickly show you what I did in main. So I initialized an SR latch to call this, initialize the values using .q and .q bar because they're not pointers. And then I print out the initial values in main, and then I call it SR latch struct test, passed it by reference, which is as what you see here in our function declaration. Struct test, I'm passing it by a pointer as I've shown you before. So then I have a number, same thing. Again, just doing all the SR latches, and it prints the values as expected. So it compiles, print the initial values, and we can go through and see our full test case. So when you're doing your programming assignment, what you're going to be wanting to do to demonstrate the different problems, you can actually use fprintf and say this is 2.1, and then call your test function. This is problem 2.2, and call your test function. What should happen is as I run your code, and I'm looking to see what your code does, it should be pretty obvious which one is which. The easier you make it for me to find out what your code is, the easier it is for me to give you points. So we want to take full advantage of that. Now, we were talking about latches, and that they're level sensitive. We want to use these edge sensitive flip-flops. We're going to talk about SR flip-flops here in a second. Now, the difference between an SR latch and an SR flip-flop is the same finite state machine, but the difference is we have this edge input, E. Sometimes you'll see it as clock, as I'll show you the logic symbol down here in a second. But you have two AND gates, and it only happens when you have your edge is equal to 1 and set a reset. Otherwise, you're just going to get 0 like normal. Now, this eliminates your, it basically makes it a positive edge triggered flip-flop. So, if I wanted to make this a negative edge triggered flip-flop, you can make it an AND gate. So that way, you have 1 and 1 here, you're going to get 0, and you could do some sort of inverter to fix it. But it would have to be, if you had a 0 on the input, you're never going to get the correct value. So we go to our truth table, edge, set, and reset. And when edge is 0, I don't care what everything else is. I want Q and Q bar to stay the same. And so then when edge is 1, what you're going to notice is it's just the exact same truth table for set and reset as before. Again, state remains the same. Reset, Q is equal to 0, Q bar is equal to 1. Set, Q is equal to 1, Q bar is equal to 0, and it's 1 and 1, then it's undefined. And then the logic symbol, which those of you can't see below, I can just draw it up here so we can. So you're going to have an S. You can either call it E or clock. Sometimes you'll see in diagrams you see this little triangle, and you have a reset value here, and then your output's going to be Q and Q bar on the outputs like so. And so now we can, let me go back up here. Let me ask you this question. All right, so if I wanted to take the previously coded values that we've done in C and design an SR flip-flop, what would be the easiest way to do it? All right, so we have our FSM, right? And why do we use the FSM instead of the NOR gates? Well, the positive edge is what we're doing here. But what was our issue? I showed you that Vhdl simulation. What was our issue? Race conditions, right? So we created this finite state machine because we have a loopback, right? Because this is a sequential element. But, so this, I have this coded here. What else in this circuit do I already have coded? Or you already have coded by the time you do this? Once you guys solve this, I can. AND gates, right? There you go, good. So I've got my AND gates coded, I have my finite state machine coded. Now, why could I use my AND gates here, but it was unadvisable to use the gates there? What's the difference? I heard someone say it. What's the difference? What's going on here that's not going on here? No. What's the name of the section?
Finite state machine.
Yeah. So what does a finite state machine consist of?
Finite state and
Starts with an S.
state.
No. They all stand. What is this? And this is when you go to interviews, you should know that this is a sequential circuit. So we go back to 4.9, we'll explain this, and then it'll be the last parts of section 3 and then through 4.9. But what we do, that's SR latch, that's SR. So we already have our finite state machine. Since those AND gates don't have a sequential feedback, then it's perfectly permissible to just have an SR flip-flop, pass our latch, and then just add AND gates to it. And so now you build a flip-flop, an edge-triggered flip-flop. And then last thing, I did my test. Here that way when you guys are doing this later reviewing it, I'll quickly show the code. And then you print them out, it compiles. And as you can see, and this is the important thing, we'll start with D-latches next lecture. Notice how when I had the clock equal to 0, that no matter what kind of manipulation I did, the initial values stayed the same. Whereas now I set clock equal to 1, and I even had it print out that. Now the values are changing. So it's going to be the rest of section 3, and then, which I believe was like 3.25 through 3.26, and then 4.1 through 4.9, and examples 3.4, was it 5 and 6, or 4 and 5? I'll look them up. Not due until Thursday. So, next time I see you all, exam time. Give me a split second. Yeah, 12:30. Yeah, we'll meet downstairs.
Okay, I'm part of your research team now.
You are. So if you want to do a thesis with me, then you're part of the team.